During these, I think, last 3 sessions, we have started to talk about the one mode of the heat transfer, or which is convection heat transfer. We started our discussion to introduce you what is the convection. We introduced different type of the convection, which we classified in terms of the fluid flow, in terms of the its flow around something or in something, and we categorize it as an internal flow, external flow, and also forced and natural convection. In previous session, we discussed about the natural convection, how is it and why it is happening, and how we can calculate the heat transfer by convection for different geometries. I told you that the reason for this natural convection is the buoyancy force and its interaction with the friction force between the fluid and the object. And we also had some example in previous session about this natural convection around different objects, if you remember. Today I am going to continue our discussion about this natural convection inside enclosure. If you don't know enclosure, what is enclosure? Enclosure is actually the helpful object actually, which mainly are being used for the electrical circuit, and those components are mainly inside these enclosures. So the temperature of the inside of this enclosure is important. In this enclosure actually, which you can see an example of that here, we don't have any pump or any fan usually. If we have a pump or fan inside that, like our laptop for example, can be encountered as the enclosure, the circuit, the electrical component are inside that, but we have a fan for that, so it is forced convection. For the laptop, because it is a compact form of the this arrangement of the electrical components, these electrical components, so we need this fan to use the forced convection. But for the enclosure with bigger or with bigger size, usually we don't use fan, and the convection or heat transfer inside that is due to the convection and movement of the or motion of the fluid inside the enclosure due to the that buoyancy and friction forces between the surface of the enclosure and the fluid inside that. So it is important to know how is the heat transfer inside this kind of the object. As you can see here, we have hot surface and cold surfaces. For example, this is hot surface, this is cold surface for an enclosure, and you can see the flow and the motion direction of the fluid inside the enclosure, and this is due to the that buoyancy and friction forces we have already introduced in previous session. Due to this motion of the liquid near the surface of this enclosure, you know that we will have the convection heat transfer. So how we can calculate the heat transfer by this convection heat transfer? Actually, it depends on some characteristic of the enclosure. It's the geometry, it's orientation actually. As you know, if this is a vertical enclosure actually, if this is a ground gravity, gravitational acceleration, or gravity force is in this direction. And as I told you, the reason for that buoyancy force is this force. So we usually should know the orientation of the enclosure against the ground or horizontal line. We should know how is its orientation. It is effective on the forces on the fluid inside the enclosure, and it is also effective on the its heat transfer. So if you remember, we had Rayleigh number to know if how is the fluid flow inside fluid flow for natural convection or natural flow. We use this Rayleigh number to know if the fluid flow is turbulent or laminar. For the enclosure, we should use this equation to calculate this Rayleigh number. And this LC, if you remember, it's the characteristic length. We need that to calculate this Rayleigh number, which is distance between the hot and cold surfaces for enclosure. So for enclosure, this LC, which is important characteristics for the calculation of Rayleigh number for the natural convection. For the enclosure, it is LC. And in this equation, T1 and T2 are the temperature of hot and cold surfaces, as you can see here. So LC is distance between these two hot and cold surfaces, and T1 and T2 is temperature of those two surfaces. PR is Prandtl number, G is gravitational acceleration, V is the kinematic viscosity, and beta, which already introduced you, is the expansion coefficient, volumetric expansion coefficient. We had that in previous session. So we can calculate Rayleigh number for enclosure with these geometries and temperature in the surface, different surfaces. Then we should calculate this Rayleigh number. If it is higher than 1708, the natural convection is actually laminar. And if it is higher than, if it is higher than 1708, we have natural convection currents. So first we should check if we have this current or not. If the motion of the fluid inside the enclosure is its Rayleigh number is higher than 1708, it has a natural convection current. You know that if the fluid inside this enclosure is not in motion, it is actually no fluid motion, the heat transfer will be only due to the conduction. Okay. So we should first check if we have natural convection current or not. We should calculate Rayleigh number. If it is higher than 1700 something, we have this natural convection current, so we will have a convection heat transfer. If it is lower than that, the motion of the fluid is not that much to have heat transfer by convection. And also, if the Rayleigh number is higher than 3 times 10 power 5, this fluid flow is turbulent. So we can use this Rayleigh number to know if we have natural convection or natural heat transfer. Then we can use this Rayleigh number again to know if the fluid flow is laminar or turbulent. And to find this Prandtl number, or beta, beta, if you remember, was equal to 1 divided by T, or temperature. So that T should be T average, which is T1 plus T2 divided by 2. T1 and T2 are the temperature of the surfaces. And you can see here how is the convection or the fluid flow inside the enclosure. And you can see when the hot plate at the bottom, it is something like this, but when the hot plate is in top, it is like this. And you can see the difference between these two. This is a heavy fluid. So when the top surface is hot, the fluid motion is not that much to have convection heat transfer. So we have only conduction heat transfer. And if you remember, conduction heat transfer means Nusselt number equal to 1. So for a heavy fluid, if we have a heavy fluid in the enclosure, the motion of the fluid inside the enclosure may not be that much to have a convection heat transfer. How we can understand that? By calculation of this Rayleigh number. So in all enclosure, we don't have for sure the convection heat transfer. We should check if the Rayleigh number is higher than this much. Okay, now let's introduce you a new parameter, which is effective thermal conductivity. As I told you, when we have an enclosure which the fluid inside the enclosure is not in motion, we don't have convection heat transfer. All of the heat transfer is by conduction. So we can calculate this by this equation, Q dot by conduction. You remember this equation, Fourier's law. To calculate the conduction, we have two surfaces with different temperature, hot and cold, a medium between them, which is the fluid, but it is in not motion. Then we can calculate the conduction heat transfer for that fluid. We know the temperature, and you'll see the characteristic length. We can calculate this conduction heat transfer. And K is the thermal conductivity of the liquid or the fluid. But when it is in motion, the fluid inside enclosure is motion due to its characteristic. It is a light fluid, and its Rayleigh number is higher than 1,100 something. So we have convection heat transfer. We can imagine that this convection heat transfer has increased the thermal conductivity of the this enclosure or this object. In other words, we can just find a new thermal conductivity for our system or for the fluid. If we encounter or also calculate the convection heat transfer, we should use this equation. You remember this is Newton's law for cooling. Q dot equal to HAS T1 minus T2. T1 and T2 temperature of the surfaces, AS the surface area of the heat transfer, and H convection coefficient, which is always our question, and we should find that. You know that it is equal to K Nusselt number divided by characteristic length. If you remember from the previous session, H is equal to K, or thermal conductivity, times Nusselt number divided by LC, or characteristic length, as you can see here. So we should know the Nusselt number. But we can define this by this equation as well. And instead of the K, we can put K effective equal to K Nusselt number. So I mean, instead of to say we have a convection, we can say we have a still conduction, but the conduction, the thermal conductivity of the fluid is changed from K to K effective, which K effective is equal to normal K times Nusselt number. So as you may guess here, if the Nusselt number is equal to 1, which means that K effective is equal to K. Nusselt number equal to 1 means we don't have convection, and all of the heat transfer is by conduction between these two surfaces and through the medium, which is liquid between them. And the Nusselt number for this condition usually can be calculated by this equation, Nusselt number equal to C Rayleigh number power n. But it is only usable for the some special cases where we have a narrow, it is applicable for a narrow range of Prandtl and Rayleigh number to find these Nusselt numbers. So usually we should find Nusselt number for enclosure to find the heat transfer by this equation. Okay, now let to calculate the Nusselt number for the enclosure with different geometries and different orientation. In terms of the orientation of the enclosure, they can be categorized to three types: horizontal rectangular enclosure, inclined, which has a tilt angle with the ground surface or horizontal line actually, and vertical rectangle enclosure. Now we will see how we can calculate the Nusselt number for these three different types of the orientation of the rectangular enclosures. As you can see here, we can find Nusselt number for an enclosure with this orientation and configuration. You can see that enclosure is enclosure here is a horizontal rectangular enclosure, and it has two surfaces with different temperature, and also the surfaces are isothermal, and temperature of the bottom surface is higher than the top surface, T1 higher than T2. So we have heat transfer from the bottom surface to the top surface, Q dot. Now we are interested to calculate this Q dot. As I told you, we can use this equation, but we need to know how much is Nusselt number for that. How we can calculate the Nusselt number? By the equation which are shown here in this slide. As you can see, Nusselt number can be calculated by this equation when Rayleigh number is between these two values, 10 power 4 to 4 times 10 power 5. So when the Rayleigh number, which we have already calculated by this equation, if it is between these two values, then the Nusselt number for the enclosure, horizontal rectangular enclosure, can be calculated by this equation. If its Rayleigh number is higher than the 4 times 10 power 5 until 10 power 7, we should use this equation. These equations are for air actually, with the Prandtl number between 0.5 to 2, but it can also be used for other gases which their Prandtl number is between these two values. So Prandtl number also can be found from the table, which for the T average. And we should use this equation for the material like water, silicone oil, and mercury. We should use this equation. We should check their Rayleigh number. If it is between these two values, 3 times 10 power 5 and 7 times 10 power 9, then if this condition is satisfied, we should use this equation to calculate the Nusselt number for these fluids. Then use that Nusselt number to calculate heat transfer. And also, this equation, which is a general equation, we should use this equation when the Prandtl number is a moderate Prandtl number. Actually, moderate Prandtl number means Prandtl number not very high, not very low. Then we can use this equation to find Nusselt number for different fluid or different liquids actually, when their Rayleigh number is lower than 10 power 5. So as you can see here, you should check this condition. You should calculate the Rayleigh number. You should find the Prandtl number for that specific fluid, liquid or gas. Then find the appropriate equation to calculate this Nusselt number for the enclosure with these characteristics. And just notice that in this equation, we should only consider positive values for this calculation inside the brackets. And this equation is valid when Rayleigh number is lower than 10 power 8. All of these equations to calculate Nusselt number are for the condition which the temperature of the bottom surface is higher than the temperature of top surface. When the hotter plate is at top, in other words, T2 is higher than T1, opposite of this, the Nusselt number is 1. Why it is 1? Because we don't have any fluid motion actually. Then we don't have any convection heat transfer, and all of the heat transfer is by conduction. So all of these conditions are important, and you should check to use this different equation to calculate convection heat transfer for horizontal rectangular enclosures. Okay, what about the inclined rectangular enclosures? As you can see here, the geometry is similar to the horizontal, for example. As you can see here, there is the characteristic length, which was the distance between the surfaces with different temperature, is still L. The surfaces with different temperature, T1 and T2, you can see when the bottom surface actually is hotter than its temperature is higher than top surface. So we will have a heat transfer like this. We should check it if it is convection or not. We should calculate Rayleigh number for that actually. So for an inclined rectangular enclosure with the characteristic like this, which it has a tilt number as theta, as you can see here, we can calculate Nusselt number by this equation. In this equation we have Rayleigh number, which you should calculate by the equation I showed you. Cosine and sine of theta are important, so you can use this equation to find the Nusselt number when the Rayleigh number is lower than 10 power 5 and this theta is between 0 and 70 degree, and also the aspect ratio, which is a new parameter for enclosure. We didn't have that for the horizontal enclosure, but for the inclined rectangular enclosure we have this aspect ratio. Also it is important. Aspect ratio means we should find that by dividing the different widths and lengths of the enclosure to each other. As you can see here, H is in this direction, or normal to the heat transfer direction actually, and L is the distance between two surfaces with different temperature, or parallel to the heat transfer direction, convection heat transfer direction. And so we should also calculate this H divided by L. If it is higher than 12, we can use this equation to find Nusselt number. Then by using this Nusselt number, find the convection heat transfer. And if H divided by L is lower than 12, as you can see here, from 1, 3, 6 until 12, you can see here, we will have a critical angle actually. You can see here and for this critical angle actually we have different equation to calculate Nusselt number. You can see here, for example, if theta is between 0 degree to theta critical, which this theta critical can be found in this table, and this theta critical also is dependent on the aspect ratio, then we can use this equation for that. If theta is between, for example, if aspect ratio is 1, this theta critical will be 25 degree. So imagine theta is between 0 and 25 degree, and then we can use this equation to find Nusselt number. And as you can see, the Nusselt number in this case is defined according to the Nusselt number for other orientation actually. Nusselt number for in this case is equal to Nusselt number for the condition when theta is 0 degree. When theta is 0 degree means in previous slides you can find that, times this division, which is Nusselt number for when theta is 90 degree. When theta is 90 degree is can be found in next slide I will tell you, which is for vertical rectangular enclosures, divided by Nusselt number when theta is 0 degree or horizontal enclosure actually, times sine of that, power these values, which are the angle of the or orientation of that, which is theta critical, and theta, which is a real tilt angle actually. And when this theta is between theta critical and 90 degree, for example, when h divided by L is 1 and theta is, for example, 30 degree, then we should use this equation. Nusselt number is equal to Nusselt number for the enclosure when theta is 90 degree, or vertical enclosure times sine theta power 1 divided by 4. And when this theta is between 90 and 180 degree, for any aspect ratio, we can use this equation to find Nusselt number, which is also defined according to Nusselt number for vertical rectangular enclosure. We will see in next slide how to find this Nusselt number for vertical. This is Nusselt number for vertical enclosure. So you can see here the Nusselt number for inclined rectangular enclosure is dependent on the two important parameters. One of them is theta, the other one is the aspect ratio, which is according to dimension of the enclosure. So when you have inclined rectangular enclosure, you should check its aspect ratio. If aspect ratio is higher than 12, you should use this equation after checking the really number. When the theta is when the aspect ratio is less than 12, then you should use this equation for different angle actually. So the Nusselt number for inclined rectangular enclosure should be calculated according to the aspect ratio and this tilt angle. I told you about this Nusselt number for when theta is 90 degree. When theta is 90 degree, actually we have vertical rectangular enclosures. Nusselt number for this type of the enclosure can be calculated by this equation. You can see here how is this vertical rectangular enclosures. Again, the distance between two surfaces with different temperature is L, and in the normal to that L we have H, and also T1 is higher than T2. So we will have a convection heat transfer in this direction. How we can calculate that? By the Newton's law of the cooling, but we need to know the H. To find the H, we should use the Nusselt number. So Nusselt number for enclosure, which is vertical rectangular enclosure actually, we should use this equation, which is also valid when the aspect ratio H divided by L is between 1 and 2, and for any Prandtl number actually. And also we should check this condition. If it is satisfied, we can use this equation to find the Nusselt number for enclosure with this orientation. And when the aspect ratio is between 2 and 10, and for any Prandtl number and with real number less than 10 power 10, we should use this equation to find Nusselt number. So as you can see, this is also is a Nusselt number for the when the theta is 90 degree. You can see, if you remember in this slide, theta is this angle. So when it is 90 degree, it means vertical rectangular enclosure. So for vertical rectangular enclosure, we can use these two equations with these conditions to find the Nusselt number. always we should calculate Rayleigh number. We should find Prandtl number for the average temperature of T1 and T2. Then we can use this equation or this one according to the geometries of the enclosure. And for other geometries, when this aspect ratio is between 10 and 40 and the Prandtl number is between 1 and 2 times 10 power 4, and also Rayleigh number is between 10 power 4 and power 7, we can use this equation to find Rayleigh number. So you can see for the vertical rectangular enclosure, we have this equation to find Nusselt number, which is also dependent on the aspect ratio, Prandtl number, and also each one of them has a specific condition. You should check if it is satisfied or not. First, it is better to start with the aspect ratio. If aspect ratio is in this range, you can see aspect ratio between 1 and 2, you may use this equation if this condition is satisfied. If H or aspect ratio is between 2 and 10, then you may use this equation to find Nusselt number if Rayleigh number is lower than 10 power 10. And you can use this equation when aspect ratio is between 10 and 40, but again you should check Prandtl and Rayleigh number for this enclosure. And this equation also same, you should check the this characteristic. As you can see here, it is a general equation when the aspect ratio is from 1 to 40, but for Prandtl for the liquid with the for the fluid with the Prandtl number between 1 and 20 and Rayleigh number for these two values. And as I told you, to find this Prandtl number especially, you should use average temperature T1 and T2 divided by 2. Okay, so for the enclosures, we had these three different orientation actually: horizontal, inclined, and vertical. And we had different equation to find Nusselt number, then use the Newton law for cooling to find the convection heat transfer. Okay, now let's see an example how we can find the heat transfer in an imaginary enclosure. Is there any question up to here, class? Okay, thank you. I'll continue. Okay, in this example, we are going to see convection heat transfer for a double pane window. If you remember, we had examples for this heat transfer for double pane with the air or any other gases between the those different different number of the glasses actually, which usually are 2. This is the double pane window. You know that it has 2 different glass, and usually air or other gases are between them. We had an example in previous chapters that we calculate the conduction heat transfer for this window actually. Now we are going to see if we have also convection for this window. If you see this image, there's a figure, you may understand that which is this window is actually a enclosure. 2 different surface with different temperature and fluid between them. So if we have if the motion of the fluid in this enclosure, which is a double pane window, is enough to have a convection heat transfer, we should also calculate the convection heat transfer plus the that conduction. So if the air is in motion naturally due to the temperature difference between these two surfaces, then we have the convection heat transfer. Let's see what information we have. The vertical 0.8 meter high, 2 meter width wide double pane window shown in this figure consists of 2 sheets of glass separated by 2 centimeter air gap at atmospheric pressure. So we know this is our glass, we know the dimensions, and also we know the air is between these two surfaces. If the glass surface temperature across the air gap are measured to be 12 degrees Celsius and 2 degrees Celsius, so the temperature of the surfaces is 12 and 2 degrees Celsius. T1 12, T2 2 degrees Celsius. Then we should determine the rate of heat transfer through the window. Okay, so we have two glasses of a double pane window which are maintained at a specified temperature. Then the rate of heat transfer through the window should be determined. First, let's see how we can find a solution for this and how we can find the rate of heat transfer. If we imagine some assumption for this double pane window, we can use our equation. First, there is a steady operating condition exists. As you may know, the temperature is changing during this heat transfer, but it is mentioned that the temperature is constant during this process. If temperature is not constant, this 12 and 2 is changing, and all of the calculation is very complicated. But we can imagine that a steady operating condition exists, and 2 air is an ideal gas. Then we can use our table to find its characteristic. And also radiation heat transfer is not considered. It is also important. So we have only heat transfer by conduction or convection we should see. Then first let's find the properties of the fluid, which is air. As I told you, usually for this as it is like an enclosure, we should use T average to find the characteristic of the fluid. Here the fluid is air. T average is T1 plus T2 divided by 2, T1 and T2 12 and 2 divided by 2, 7 degrees Celsius, and the pressure is also mentioned, 1 atmosphere. Then we can go to table A15 to find its thermal conductivity, its kinematic viscosity, its Prandtl number, and also the volumetric expansion coefficient, which this volumetric expansion coefficient, if you remember, is equal to 1 divided by T, which T average of the air, and also it should be in terms of Kelvin. Okay, so now we have the property for air, which is our fluid in the enclosure. Then we should find heat transfer for that. If you remember, we always use this equation to find the convection heat transfer. Okay, first let's see how much is Rayleigh number for that, to see if we have a natural convection or not. To calculate Rayleigh number, we should use this equation. And also you can see here we don't have a forced convection, it is natural convection, no pump, no fan. So we have only we may have only natural convection. We should check. Then we can calculate, we should calculate Rayleigh number, then compare with that value I told you, 1700 something. Okay, Rayleigh number is equal to G beta times T1 minus T2 times LC power 3 divided by power 2 divided by PR times PR, or Prandtl number. All of the information are already known. By substitution, we can find this Rayleigh number, and as you can see here, Rayleigh number is 1 times 10 power 4. It is much higher, 1700. So we will have the convection heat transfer, or natural convection heat transfer actually. Then, as you can see here, it is a vertical enclosure. How we can find the rate of heat transfer for that? By this equation, which we need to know how much is its Nusselt number. How we can find Nusselt number for the enclosure with these characteristics? As I told you, and you can see in this slide as well, we should find its aspect ratio. How much is aspect ratio for our example? H divided by L. What is L? L was the distance between two surfaces. And H is the normal direction to that L. So H divided by L, the dimension also are given. So H divided by L, or aspect ratio, will be 40. Then the Nusselt number in this case can be determined from this equation. According to this slide as well, we should use this equation to find the Nusselt number. We have Prandtl number, we have Nusselt number. Let's see for when aspect ratio is 40, which equation we should use. Okay, you can see here, this one cannot be used, this one cannot be used. We should use this equation when the aspect ratio is between 10 and 40, which is 40 here. When the Prandtl number is between 1 and 2 times 10 power 4, okay, our Prandtl number is this much. Close to the 1 actually. And also the Rayleigh number between these two values, 10 power 4, 10 power 7. Let's see our Rayleigh number. Yes, 1 close to this value, actually higher than that, in this range. So we should use this equation to find the Nusselt number. So we can find the Nusselt number by this equation. Rayleigh number we have already calculated. Prandtl number we know that from the table. Aspect ratio we have calculated. So the Nusselt number after calculation will be 1.4. So we have a Nusselt number. Then we are going to use this equation. We had this in previous slide to calculate the rate of heat transfer by natural convection. We need also AS. What is AS? The surface area of convection heat transfer, which is H times the width of that, which is also given 0.8 times 2 meter. So AS will be 1.6 meters square. By substitution in Newton's law, we will find the convection heat transfer. So the rate of heat transfer will be 27.1 watt for this double pane window. Okay, so in this example you can see how you can use this equation to find the Nusselt number for a rectangular enclosure. For other enclosure also you should check the conditions, then find the Nusselt number, and finally use this equation to find the rate of heat transfer. Okay, now let's see for other geometries how we can find the rate of heat transfer for those geometries. One of the common geometries is these concentric cylinders, as you can see here, two cylinders put together like this with this diameter actually, and between them we have some kind of the fluid between these two different surfaces. The heat transfer is between the outer surface of the inside the tube or cylinder and inner surface of the outside or outer cylinder. And temperature of these two cylinders are different. Outer cylinder temperature is TO, which is different from the temperature of the inner cylinder, which is TI. So this geometry and orientation is two concentric horizontal isothermal cylinders. Now we are going to find out how is the heat transfer or natural heat transfer for a geometry like this. The rate of heat transfer for an object with this configuration and geometry can be defined by this equation, which is natural convection per unit length actually. And as you can see here, DO, DI are the diameter of the two cylinders, diameter of the outer cylinder, diameter of inner cylinder, DI, and these two are the temperature of those two cylinders. And 2 pi K effective for this object can be defined by this equation. K effective divided by K, which is thermal conductivity of the fluid, and Prandtl number should be you should find it from the table for the temperature of the average temperature actually. Again, to find the Prandtl number for the fluid in these concentric cylinders, you should go to the table. Different tables for different fluids, for example. Then there you need to know the temperature of that fluid, and the temperature of that fluid is equal to the average temperature of these two cylinders. So K and Prandtl number from the table. Rayleigh number you can calculate by the equation, which is the general equation for Rayleigh number. We have had that in previous slides. The only thing is that to calculate this Rayleigh number, you should know how much is the characteristic length. For this object, this geometry, the characteristic length is equal to DO minus DI divided by 2. Diameter of the outer cylinder minus the diameter of the inner cylinder divided by 2 will give you the characteristic length, which is actually the distance between two surfaces of these two cylinders, this part actually. So the characteristic length also can be calculated by this equation to find the Rayleigh number. Also, we have here a new concept, which is geometric factor. You should put in this equation to find the K effective, and also to find if you can use this equation. This geometric factor for cylinder or concentric cylinders can be calculated by this equation. F for cylinder or geometric factors for concentric cylinders can be calculated by this equation, which is dependent on the diameter of the two cylinders and characteristic length, which can be found by this equation. So to find the rate of heat transfer through the annular space between the cylinders by convection, by natural convection per unit length, You can use this equation. You need to know how much is K effective. You can find K effective here. To find the K effective, you need to know the this geometric factor for concentric cylinders. This F for cylinder can be found from this equation, which is only dependent on the geometry of the these concentric cylinders. And also we have some special cases when these F cylinder times Rayleigh number is lower than 100, natural convection current are negligible and the K effective will be equal to K. In other words, we don't have natural convection. So you can check if this value is lower than 100, we don't have any natural convection current. And also notice that the K effective cannot be less than K. K is the thermal conductivity of the fluid here. Okay, when we have convection, this thermal conductivity may be increased, but it cannot decrease. So when in our calculation K effective divided by K is less than 1, we should ignore that and we should only put K in our equation, which finally it will be equal to the conduction heat transfer actually. So for the concentric cylinders, you can use this equation to find the rate of heat transfer by natural convection. And also for concentric spheres, again we have similar equation to find the rate of heat transfer by natural convection. As you can see here, it is dependent. This is two concentric isothermal spheres with different diameters. Di for the inner one and the O for outer one spheres, and their temperature, or in better words, their surface temperature, which is isothermal surfaces, will be Ti and To. Then also we have a fluid between them. We are interested to know how much is the natural convection heat transfer between these two surfaces and that medium or liquid or the fluid between them. We can use this equation like for the concentric cylinders. Again, as you can see here, we need to find this K effective. K effective again can be found by this equation. K is the thermal conductivity of the fluid, which can be found from the table. Again, for the average temperature, Ti plus To divided by 2, you should find the thermal conductivity for that. Also Prandtl number for that value of the temperature. And the Rayleigh number. To find this Rayleigh number, also you need that thermal conductivity Prandtl number, and also these characteristic lengths. Characteristic length for this case, as you can also see here, is dO minus di divided by 2. Actually, it is the distance between the surfaces with different temperature, this LC. So you can find the Rayleigh number by this LC and beta and other information which can be found from the information about the question. And also you should check these values. The Prandtl number should be between 0.7 and 4,200, and also this is also geometry factor for the sphere. How you can find this geometry factor for this concentric sphere? By this equation. Geometry factors for concentric sphere can be found by this equation. Again, characteristic length divided by this relationship between the two diameters, and as you can see, it is only dependent on the geometries of the two spheres. And like what we had for the concentric cylinders, if K effective divided by K is less than 1, we should set K effective equal to K, because when we have convection, a natural convection, the heat transfer should increase, not decrease. We don't have a reduction in the heat transfer or the thermal conductivity actually by due to convection. So when K effective, this one is K effective divided by K less than 1, we should just put K effective equal to K. In other words, K effective equal to K should be. And the final slide actually for today's session is this one, which is combination, how to calculate rate of heat transfer when we have a combination between natural convection and radiation. As you can see in this figure, let me make it bigger. Okay, as you can see in this figure, for example, we have two concentric cylinders, and as you can see, the outer cylinder is transparent and inner one is opaque, which is aluminum tube, and the outer one is a glass cover actually. So between these two will be fluid, for example, and temperature of those two surfaces will be if it is different in different temperatures, then we will have convection heat transfer between them. And also, if there is a source of the radiation energy, we will have radiation heat transfer as well, because the radiation energy will reach to the inner surface, actually inner cylinder, and it will increase its temperature, and finally we will have a heat transfer by radiation. In this case, to calculate the total rate of heat transfer, we should find rate of heat transfer by convection or natural convection, and also rate of heat transfer by radiation. And if you remember in previous sessions, we should use this Stefan-Boltzmann equation to find radiation heat transfer, which is dependent on the emissivity of the object surface, and also the surface area of heat transfer, and the temperature of the surface of the which is receive that radiation, or TS, minus T surrounding, which is the temperature surround that object. So we should calculate this radiation heat transfer. Then for two parallel plates, actually, we can use this equation to find the rate of heat transfer. So this is a general equation to find rate of heat transfer for a surface with this temperature of the surface and surrounding. But when we have two large parallel plates, we should use this equation to find the radiation heat transfer between these two large parallel plates, like what we have here. Then this part, which is a new part actually, we can rewrite like this as the effective emissivity. As you know, the radiation heat transfer is extensively dependent on the emissivity of the surface. So this effective emissivity also for that two large parallel plates can be found by this equation, or epsilon effective equal to 1 divided by epsilon 1 and epsilon 2 are the emissivity factor for those for the surfaces of those two large parallel plates. And as you can see here, if we have T infinity minus Ts and T surrounding higher than Ts, the convection and radiation transfer will be in opposite direction, and they should be subtracted from each other. In other words, the direction of the heat transfer is important, and if we have this condition, the radiation and the convection heat transfer will be in opposite direction. When T infinity minus Ts for the natural convection from surface to surrounding, when T surrounding is higher than Ts from surrounding to the surface. So finally their directions will be in opposite, and they should be subtracted from each other. About the radiation heat transfer, we will have in-depth discussion in next sessions. I have already prepared the videos for radiation, and I will upload and update you about them. So today we have finished actually this our discussion about convection heat transfer. This is a summary of what we have learned in this chapter. Actually, physical mechanism of natural convection. We know that we already know that the equation of motion and Grashof number, which was important to know if the flow is laminar or turbulent. Natural convection over surface we had for different geometries and orientation, and natural convection inside enclosures also we calculated this natural convection for different enclosure, for the rectangular enclosures and also the concentric cylinder and spheres, and also we introduce how to find the rate of heat transfer for when we have a combined natural convection and radiation.